Hello, everyone. I'm Gary Ma from Harvard. Today, I'm really excited to share with you our work, Platform Equilibrium, Analyzing Social Welfare in Online Marketplaces. This is joint work with Alon from Hebrew University of Jerusalem and my advisor, David Parks. During COVID, many cities were at lockdown. Residents were forced to stay at home, and restaurant and other brick-and-mortar businesses had to close down. So some people were very pessimistic in terms of the economic impact of COVID and estimated that US GDP could have fallen by 40%. Naturally, workers and business owners were wondering if there's anything that could save them from the financial ruin. We could say that because of COVID, buyers could no longer access the sellers anymore, so there's no trade that's possible. But however, with these online platforms, with their delivery service provided, they re-enable the buyers to access the seller and re-facilitate the trade. The limited access between buyers and sellers are not only limited to during the COVID period. Even right now, buyers have limited access to sellers. In this example, the second buyer, David, although he likes chocolate cake very much, but because he doesn't have a car and the store for chocolate cake is very far away, so he cannot access the chocolate cake. But there is a macaron place just downstairs of his office, so he could access the macaron place. Now again, with the delivery platform, the chocolate cake store could deliver the chocolate cake to David. So platform connects the buyers to sellers. In the meantime, the platform are revenue optimizing entities, and per trade, they charge a commission fee that typically ranges between 15% to 30%. And sometimes this commission fee could be way too high for the restaurant to bear. The restaurants, as a part of the traditional catering industry, have a profit margin from 7 to 22%. So they have to face with a difficult decision. Either they join the platform, in which case they are faced with very, very hefty delivery fees, or they do not join the platform and they lose their buyers. So regulators are aware of this, and they posed commission fee cap to increase the market efficiency. For example, the state of Massachusetts, as well as the city of San Francisco, posted a 15% delivery fee cap. But the second day that the Jersey City imposed a delivery fee cap of 10%, Uber Eats set a $3 delivery fee to the local orders. So we start to see this three-sided interactions where restaurants are deciding whether they want to join the platform or not, and the platform are trying to pose commission fee to maximize their revenue. At the same time, they can bring together buyers and sellers to increase market efficiency, but taking a portion of that as their own revenue. And the regulator who seeks to maximize market efficiency bring the buyers and sellers together as much as possible. In this project, we seek to analyze the effect of incentives of optimal revenue platform on the market efficiency. On a high level, we view the market as a graph and we study it in a two-stage game. There's a monopoly platform that sets revenue optimal commission fee. Sellers choose to join the platform or not. If they decide to join the platform, they can access all the buyers. And then market clears, seller decision will form an equilibrium. Our two high-level questions that we ask is, one, to what extent do revenue maximizing platforms enhance market efficiency? The question is not too obvious to answer, not very obvious to answer, because on the one hand, the platform can increase commission fee so that fewer sellers will join the platform, in which case market efficiency goes down, but the platform can extract more revenue per trade. On the other hand, the platform can pose a lower commission fee so that there's lower revenue per trade, but then more sellers will join the platform. Our short answer to this question is platform incentives and welfare can be very much misaligned. The second question asks, how does regulation help with improving market efficiency? And our short answer is, under slight regulation on commission fee, robust welfare is guaranteed. Here's our model. There's some unit demand buyers and unit supply sellers. And the market we view as a bipartite graph. Unit demand are very easily generalizable to more general settings, but for the sake of this talk, we're going to stick with unit demand. There are two types of edges, active edges as well as inactive edges. Active edges are highlighted in blue, and those are the edges the buyers could access to the sellers, even without the platform. Inactive edges means the trade that could only occur with the platform. Now, without a platform, transactions can only take place via the active edges, and a Warasian equilibrium is formed. We use the highest Warasian equilibrium price to reflect the dominant power position of the platform to extract revenue and choose equilibrium. In this specific example, the only Warasian equilibrium allocation is achieved through 3 transactions done through these 3 active edges highlighted in blue. The total social welfare is 3, which is just the summation of the 3 buyers' valuation. And each seller get a Warasian price of 1. Now, Warasian equilibrium without a platform could be very, very inefficient because the realized social welfare is only 3. But the optimal social welfare, denoted by the dotted red line, could be as high as 4.6. Now, with the platform first posts a commission fee, for example, 25%. Each seller will decide whether to join the platform or not. If a seller decides to join the platform, in this case, the chocolate cake factory, then it's going to be connected to all the buyers. Again, a Warasian equilibrium is formed. In this example, the final Warasian equilibrium allocation is realized through buyers number 2, David, purchased from the chocolate cake place at a price of Warasian equilibrium price 2.3. The third buyer, which is myself, purchased from the creme brulee store at a Warasian equilibrium price of 1. And because no one buys from the macaron store, macaron place has a Warasian equilibrium price of 0. Finally, 25% of Warasian equilibrium price of those sellers who join the platform will go to the platform as commission fee, namely alpha times Warasian equilibrium price of P. Now let's discuss how each seller decides to join the platform or not. Let's take the perspective of the chocolate cake. Given that the other 2 stores do not want to join the platform, it compares its own on-platform utility towards its off-platform utility. Let's take a look at 3 different cases of commission fee that ranges between among 25%, 50%, and 60%. We have already seen that the platform's on-platform Warasian equilibrium price is $2.3. Now, their on-platform utility is 1.725, 1.15, and 0.91 respectively. However, if the chocolate cake doesn't want to join the platform, it's going to be sold to the first buyer, who is Alon, at a Warasian equilibrium price of $1. So its off-platform utility is equal to 1. Now, chocolate cake only wants to join the platform when commission fee is 25% or 50%, because their off-platform utility is lower than the on-platform utility, respectively. Chronologically, in the first time step, a market is given by sellers, buyers, valuation, active edges, and inactive edges. Second, the platform chooses a revenue optimal commission fee. Third, sellers form an equilibrium in the game, deciding to join the platform or not. And a seller joins the platform if and only if their on-platform utility, which is equal to 1 minus commission fee times their on-platform price, is larger than their off-platform price. These on-platform prices, as well as off-platform prices, are determined by Warasian equilibrium price, which depends on the market structure, which in turn depends on which are the sets of sellers who decide to join the platform. So this is where the equilibrium notion kicks in. Just to remind that the platform chooses a commission fee to maximize its revenue. Here are our results. Our first result characterizes the set of equilibrium. Pure equilibrium do not always exist in general markets, but always do exist in homogeneous goods market. Homogeneous good markets are the markets where all sellers sell the identical good, but different buyers have different valuation towards this identical good. Furthermore, there exists a polynomial time algorithm to find a pure equilibrium. Our second result is our main negative result. It reads, without regulation, even for homogeneous good market, a revenue maximizing platform could induce a price of anarchy as bad as logarithmic to the number of buyers and sellers. Furthermore, this bound is tight. The price of anarchy is simply the ratio between the optimal social welfare, when all the buyers and sellers could transact with each other, over the social welfare for platform equilibrium. So the larger the price of anarchy is, the worse the market efficiency. Our third result is our main positive result. It reads, with regulation, even for general markets, as long as platforms are regulated to set a fee below commission fee alpha, the price of anarchy is upper bounded by 2 minus alpha over 1 minus alpha. Furthermore, this bound is tight. We want to stress that this is for general market, meaning the seller sells goods that are different. Put it in the context of the real world. Real world, major platform sets a commission fee of no larger than 30%. Then 2 minus alpha over 1 minus alpha will translate to welfare, social welfare is at least 41% of optimal welfare. Again, just to remind, optimal welfare is the social welfare when all the buyers and sellers can transact without friction, even without the platform. Now let's take a high-level look at the proofs. We introduce our first result to build the foundation for the second as well as the third result, as well as to gain intuition in terms of the equilibrium structure. The first result says pure equilibrium doesn't always exist. In this example, when commission fee is in a range around 0.5 or 50%, no pure equilibrium exists. Why is that? First, the chocolate cake store will want to join at alpha equal to 1/2. This would take away the only buyer that macaron has off platform. So macaron will have to join the platform. This will take the only buyer that creme brulee has off platform. So creme brulee will have to join the platform as well. But now this decreases the on-platform origin equilibrium price for the chocolate cake store. So in the end, chocolate cake store drop off of the platform, which forms a cycle. Now macaron drops off the platform, creme brulee drops off the platform, so on and so forth, and the cycle restarts. What we managed to show is for homogeneous good market, as commission fee is lowered from 1 to 0, sellers will join the platform one by one, forming pure equilibrium, and those sellers who join at a higher commission fee will never drop off at a lower commission fee because of new joining sellers. Meaning that for homogeneous good market, the above stated cycle never exists. Our second result is our main negative result. It says for homogeneous good market, a revenue maximizing platform induces price of anarchy of logarithmic to the number of buyers and sellers, which is tight. And this bound is even worse for general markets. Here's the tight example. This is a market with no active edges. The first buyer has a valuation of n plus epsilon. The ith buyer have a valuation of n over I. Because there's no active edges, the platform could pose a commission fee of 100%, and any number of sellers joining is an equilibrium. If only one seller joins, macaron number 1, platform revenue is equal to origin equilibrium price of this on-platform seller, which is n plus epsilon, which is just equal to this first highest buyer's valuation. If any I number of sellers join, where I is larger than 1, then each of these sellers will have on-platform price of n over I, which is equal to the ith buyer's utility valuation. This times the number of sellers who join the platform gives us the platform revenue, which is n. Because n plus epsilon larger than n, so the platform will choose the equilibrium where only one seller joins. This gives an equilibrium welfare of n plus epsilon, but however, the optimal social welfare is the summation of all the buyers' valuation, which is in the order of n times logarithmic n. This gives the price of anarchy of logarithmic to the n. Now, for the proof of upper bound, we're providing welfare guarantee via revenue guarantee. First, assume there's no active edges. Then again, platform can pose commission fee close to 100%. If I sellers join, then the revenue of I sellers joining of the platform is I times VI. This provides a lower bound on optimal platform revenue, which in terms provide an upper bound of the summation of buyers' valuation in terms of the optimal revenue, which leads to the upper bound on optimal social welfare, given by optimal revenue. And since optimal revenue is smaller than social welfare of the equilibrium, this is how we establish the relationship between social welfare versus optimal welfare. Now suppose now there are active edges, then building upon our result number 1, the platform can continuously lower the commission fee. In doing so, the sellers will join the platform one by one. So in continuously lowering the commission fee alpha, the platform is essentially picking some number of sellers joining the platform and picking a corresponding commission fee alpha that is not too low. In doing so, we can lower bound the optimal revenue and thus lower bound the equilibrium welfare. For general markets, we show price of anarchy could be as bad as number of the buyers or sellers. But do note that all these tight examples, these negative examples, they occur when the platform posts a commission fee 100%. But in the real world, platform won't be able to post 100% of the commission fee, either because there's market competition or there's regulations. This is why we ask, how can regulation help improve market efficiency? And our answer is, this leads to our main positive result of result number 3. With regulation, even for general markets, a revenue maximizing platform, when regulated to set commission fee lower than alpha, the price of anarchy is upper bounded by 2 minus alpha over 1 minus alpha. Furthermore, this bound is tight. We extend this result to multiple platform competitions, and we can use this result to lower bound the buyer and seller welfare, which is the buyer and seller excluding the platform part of the social welfare. Put it in the real world context. When the platform commission fee is smaller than 30%, then buyer and seller welfare is at least 37.7% of the optimal social welfare, should buyers and sellers could transact freely without access each other without any friction. Now, for a high-level proof intuition, if in a market there is a pure equilibrium where at commission fee alpha, no seller join the platform, this will mean that the edge valuation in the optimal social welfare for that seller, for all seller, cannot be very large. Why is that? Because if the edge valuation is very large, then the seller would have joined the platform at alpha and reap high revenue on platform utility as well. In doing so, we can upper bound the optimal social welfare. If we have a pure equilibrium at commission fee alpha where some sellers join, then we can construct a market of the same welfare, but with added extra additive edges. And these extra edges correspond to those sellers who join the platform at commission fee alpha. But now, with this new market, with these added new active edges, these sellers no longer want to join the platform anymore because they could already access the buyers off platform. This will revert back our case to the first case when no seller joined at pure equilibrium. For mixed equilibrium, we extend our analysis using Bayesian game. For our result 1, 2, 3, we can extend them to beyond unit demand settings. We can include the analysis when sellers have production cost, and we can also cater for multiple platforms competing with each other. And finally, we also have a following up work upon platform matching, meaning that platform uses matching tool instead of pricing tool to maximize its revenue. And then we discuss what is the incentive of revenue optimal platform, how does that affect market efficiency. To conclude, we bring forward a model to capture the interaction between 3 sides. A platform which can increase buyers and seller welfare, who bring them together, facilitate trade, but at the same time take a portion of the welfare as revenue itself. Sellers who decide to join the platform or not, based on the commission fee, and regulators who seek to cap the commission fee through and hope to increase market efficiency. And one of our results is, without regulation, a revenue maximizing platform can lead to inefficient market outcomes. But even under slight regulation, robust welfare is guaranteed. Thank you for listening.